Hi, welcome to the Earth Science Classroom. Welcome back to the videos and discussions all about Earth science and teaching. So today we're looking at the continent-to-continent convergent plate boundary. And it's in a series of the plate boundaries and plate margins where we have two tectonic plates meeting each other. And in this situation, we have two plates that are both continental, both similar densities and similar effects on isostasy. And we're going to see what happens when they collide and there is collision, and they can only go one direction, basically. So we're going to look at this video, we're going to look at the diagram and annotate it and discuss it. We're going to look at the features that are created in this kind of collision and plate boundary. We're going to look at introduced faults and where these come in. We're going to look at some metamorphic and some igneous rocks and how they fit in. And we're going to look at orogenies or orogeny, okay, in terms of the process of building mountains. All right, so here we go. All right, so let's start at the beginning. The conversion let's backtrack before these two plates collide and they actually meet. So what you have is going back to the Wilson cycle. And I did a separate video on this. If you want to check it out, there's a link in the top right to click on the video. And basically, it's from 1966. A Canadian professor, scientist, Wilson, basically devised that these supercontinents, like Pangaea, that existed about 250 million years ago, broke up, separated, okay, divided through rifting, continental rifting, the formation of oceans like the Atlantic, and that the continents would spread apart and be transported through convection currents, and thus the whole Wegener-Hess system of plate tectonics. And he stated in this theory that eventually, once they spread apart, so it's like huge, massive, like, supercontinent, it's going to divide, okay, and rift and spread apart, thus creating the different continents and different areas of the world. And eventually, like a revolution, these continents would eventually find their way back and form another supercontinent. So there's a cycle, very long, drawn out tectonic cycle of division and collision and creation of these large supercontinents. And so eventually there is a boundary between two tectonic plates whereby they're going to collide and reform into this larger mass. And this is the diagram we're looking at today. So all of these collisions, they started out with an ocean component, an ocean plate component. Whereby there was initially the ocean to continental convergent plate boundary, which again, we've done a video of this, you can check out. Again, there's a link in the top right. So there's an ocean continental boundary initially. And as that subduction zone and the trench is going to move and is going to disappear, eventually that subducting plate of ocean plate is going to be no more. The ocean is going to become smaller and smaller and smaller until it actually gets subducted away. And what's left is these large continental crusts behind it, usually next to a craton, which is a very stable and old part of the crust. And also you can talk about these shields as well, okay, which kind of were formed originally billions of years ago and haven't really changed since. What's changing are the margins, the boundaries, and ocean plates. So these colliding plates now are just continent hitting continent. And here, okay, so not to confuse it with crust. So here's my crust, here's my lithosphere, here's my crust, lithosphere, and down here we have asthenosphere, and we'll have our convection currents like this. So here, this area right here, that is our kind of like prehistoric or paleo subduction slab that is oceanic in origin. So it has some sediment. So as these are colliding, you're going to have some accreted terrain, which is transported material, and it's dumped onto this area right here where they are colliding. Okay, so this old slab that's subducting actually starts to break off because they are different densities. And it stops, and once it breaks off, this actually slows down, and it starts to, rather than just subduct, they are now similar densities, these both crusts, they're both continental. So we're looking at more granitic and andesite on both sides, looking at around 2.7 grams per centimeter cubed, which is the average. So, the sorting slab could be, basalt, which is 3, so it's going to be heavier. This lighter crust is going to be more buoyant, thus, with isostasy and mass, it's going to basically float higher and will not subduct, will not sink. It's going to collide and crash into the other one. Thus, the only real logical solution is, or the direction of movement for these two colliding plates is, some of it will go in and squeeze, and this is called crustal shortening, which we'll get to later on in a different video, or you'll have this movement up because the air obviously is a hell of a lot less dense than the rocks, and it's easier to go up than down because this is obviously more dense in the asthenosphere. So looking at 3.4 plus for the density, and it's much easier to go into the atmosphere and go against gravity basically. So going back to the subduction slab where the ocean continent initial collision happened, you're going to have some magmatic material that's formed because of the subduction. You're going to have some metamorphosis of the sediments and of the basalt, which is the main component of the ocean crust. So you're going to have your different variations of metamorphic rock from basalt, and based on temperature and pressure. Now, you're going to also have these high pressure minerals, or ultra high pressure minerals as well. And we'll get to that in a second. So you're going to have some remnants of magmatic material, some cooled magma, some intrusive magma, some granite inside. You're going to have some old magmatic material and extrusive lava or extrusive igneous rock in terms of lava on the top there as well. And right here, if I might make some room right here. Here we go. All right. So right here, do a big square. Right here, we have what's called the collision zone. Now, this is important because once we just get into pure continent versus continent boundary, and we're matching the same densities, and due to isostasy, they're going to float and resist any kind of under thrusting. Now it's going to be over thrusting. You're going to have these two plates hitting each other and basically over thrusting each other, which means one slab, one part of the rock layer, the strata, is going to be pushed up and on top of each other, thus forming a thicker and thicker crustal layer. Over the Himalayas, it can be as thick as 90 kilometers, which is insane because the average is around 25 kilometers for the continental crust. And this extreme thickness is due to the consistent collision. Right? Once they collide, they don't stop and just take a little break or have a kickback. No, they keep colliding and keep pushing. So more and more rock is added to the mix day in, day out. So it's going to keep growing, keep moving in this direction, okay, until there is a switch in the convection currents, until there's a new rifting that takes place in the future. So this is going to be an increase in mass, and you're going to form what's called an orogeny, or an orogenic belt. A long, wide, high elevation mountain range called an orogenic belt, which comes from the word orogenesis, which is orogenesis, and oros is Greek for mountain, and genesis is Greek or Latin for earth. So we are creating, seeing the birth, seeing the formation of these mountains, and this is called orogenesis or orogeny, orogeny, or in terms of a long, consistent range of this high elevation material mass for an orogenic belt. So what we have here is a fully fledged continent-to-continent boundary. You formed the orogeny, so you have the high mountains. Oh, what's that? The high mountains have some extinct volcanoes or volcanic material due to the old subduction slab, and you have faults. Now, because this is compressional stress, you usually have what's called reverse dip-slip faults. Now, dip-slip looks like this. So I have my piece of rock. All right. Now, dip-slip means a fault line or a fracture, a break. So a fault line is where you have movement around a fracture. Fracture is where the stresses has acted or placed upon the rock that has gone through deformation and it's finally broken. The rock is finally broken. We call it a fracture or rupture. And if there's continued motion or movement either side of the fracture, we call it a fault line. Okay, so this fault line, there's two different types of faults: dip slip and strike slip. This is a dip slip, so you have this angled diagonal fracture fault line, and we have the footwall, which is over here because you can draw a line down, and the arrow over side the arrow goes on is the footwall. That stays where it is. This wall is called the hanging wall, and hanging wall is going to move. In this case, it's going to move up because compressional stress acting on it, so you push up and you get some of that. Now, in particular, what you do get in these orogenic belts and these large mountains, what we call fold mountains as well, is we get thrust faults, which have an angle of dip, which is the angle of the fault line, right, of less than 45 degrees. So it is a gentle slope of the fault line, therefore it is going to be fast because it's not as steep, therefore it's not going against gravity as much, therefore the movement can be quicker over this fault line. And this is also called a ramp. We'll get to this in a different video, which is also linked at the top, thrust faults and the differences and how they're created. And you get all these different thrust faults. So these little black lines here are thrust faults where the rock has kind of like over thrusted each other and gone over each other, and that's also accumulated the mass. You see this large mass of the mountain range. So that's pretty much how we do it. Now the examples. All right, so the Himalaya mountains. All right. Classic, you've got Mount Everest, you've got basically a consistent, nearly thousands of kilometers long mountain range, longest in the world and the highest, so the roughly majority of 29,000 feet above sea level, whereas the average mountain range is about 15,000 feet above sea level. And to be termed a mountainous area has to be only an average is around 900 meters or 3,000 feet. So that is the kind of thing I saw in research that would define a mountainous area, a consistent area terrain that has a relief elevation above 900 meters or 3,000 feet. So you can see the Himalayan mountains is way above that. And also, it's classically formed through the Indian subcontinent, through a nice little journey for 225 million years, through an ancient TESC. Oh, no. TESC, which then gets consumed, smothered, reduced in size till it's not there, and the sediments get put into the softer Eurasian plate. So the Eurasian plate is collided with and is softer, weaker than the Indian subcontinent plate, and you get the collision and orogeny forming from the past 30 to 45 million years. And thus we get Mount Everest, which is currently the tallest mountain in the world, 29,000 and 29 feet, nearly 5 miles above sea level, and is an insane climb for anyone who attempts it. So that's Himalayan mountain. The Alps in Europe are another classic example. The Ural Mountains in Russia, like the unofficial boundary between European Russia and Asian Russia. You've got the Rocky Mountains in North America and the Appalachians in the eastern United States, as well as these classic examples. So USA on the west coast, USA east coast. Obviously, these are a lot smaller due to erosion and it being next to a passive margin, margin for two plates. Now, not sure what passive margin is. You can check on the top right for the for a link to the video on what this is. So there's examples. They're all around the world. These are beautiful, massive orogenic belts. These beautiful mountain ranges. Very classic terrain, classic topography, and that's how they form. So two plates colliding. Guys, hope you like this video. Please subscribe if you want to subscribe. Leave a message in the chat, the comments, be great, much appreciated, and I look forward to seeing you in the next video.